image which will actually contain the text. Okay. And if we see the image, we will not get the information about the hidden information. Okay, that we will not be able to know it. Right. So today's problem statement is write a program to demonstrate image steganography operations, embed and extract. Like encryption and decryption, here we have two operations, embed and extract. And our today's goal is to hide 1 bit per pixel. So let me explain you the theory portion first about this image steganography. Now, this is also part of your syllabus for sessional exam. Okay, so I will not cover it into the theory class. It is a simple topic, and today whatever I will discuss in the lab, the same will be part of the syllabus of the sessional exam, third sessional exam and final exam also. Okay, so I will share you that document with you for image steganography. Okay. Okay, can you see the slide? Can you see this document which I have opened? Okay, okay. Very good. So, steganography, what is a steganography? So, steganography is art of hiding messages over some medium like text, image, video, right? So, steganography is used to hide messages. Okay, that is the method. Now, the medium could be text, image, or video. Okay, and in today's lab, you will be working on image steganography. Okay, but there are techniques for text and video steganography also. So the medium is also known as cover. Okay, any of you have studied modulation technique? Modulation, any of you are aware about modulation? Amplitude modulation, frequency modulation. Right, so what is the modulation? Can anyone say? So I can, if you know that concept, then I can relate easily with this steganography. See, basically, when we want to transmit any signal, this is the fundamental concept of communication. Although it is not part of the syllabus in today's subject, in this subject, but this is the fundamental of communication. Okay, and all of you should know about it. See, in communication, the message signal frequency is raised to the range so that it is more useful for transmission, or it can be raised to the signal frequency which can be transmitted easily, right? So basically your message signal frequency may not be sufficient to transmit it at a distance. So what you do is you take the help of carrier signal. So there is a concept of message signal and there is a concept of carrier signal. So carrier signal and message signals are combined, and then at the frequency of carrier signal, the signal is transmitted. This process is called as modulation. Okay, and demodulation is that once the carrier frequency is transmitted and at the receiver end it is received, it will be demodulated. So the carrier signal is going to be removed and message is going to be extracted. This happens in our normal life also. When you want to send a message or letter, physical letter, What you do, you write a letter and then put it into the cover, and then you post that cover. So that cover is carrier and your message is inside that. Exactly same concept is in steganography. So your steganography contains a message inside a cover, and what you are transmitting is cover, but that contains the message. Okay, and that cover in our case is in image steganography is some image. So image may contain some text. Okay, so or some information. We will see that how it can be done. So steganography has two parts. Okay, so based on the cover, we have different categories like text steganography, image steganography, video steganography. Okay, steganography has two parts: embedding phase and extraction phase. And these two parts are similar to encryption and decryption. Okay, here the terminology used is embedding phase and extraction phase. So in embedding phase, as you can see, there is a message and there is a cover. So a message could be some binary information and cover could be some image. Now, as you are aware that any information in digital domain is in binary form. So your image is also can be represented by some binary information. And any of you are aware about how the image can be represented in binary? Any of you are aware about that? Pixels. Perfect. Very good, Priyank. So your image is essentially pixels. The smallest element in image is pixel. And pixel is basically representing intensity of color. Color is in the form of RGB, red, green, and blue. A combination of these three. Color as a code. Yes. Yes, correct, Harsh. But there may be a grayscale image where there is only one color. Okay, grayscale image has only one color. So you have color and you have grayscale image, this type of image, but basically it is represented as a pixel, and pixel is having intensity which has a value. If it is represented as an 8-bit value, the intensity of the value can range from 0 to 255. Okay, that is 8-bit. What is the maximum possible value with 8-bit? What is the maximum possible value with 8-bit? 2 raised to 8. What is the value? 256. So total 256 values are numbered as 0 to 255. 0 means the no intensity and 255 means full intensity. Okay, that is the minimum and maximum value. So here there is a message which is combined with the cover, and then the process of embedding actually does this combination of these two with the help of some key. Now this key may be optional or it may be used. So with the combination of these three, it provides the output which contains this message which is hidden. Okay, and this output is called as stego object. So if the cover is image, the output is called as stego image. Okay, so message is something which we want to hide. Okay, so on the extraction phase, the input is stego object. So if it is image, it is stego image. If it is video, it is stego video. Or if it is audio, then it is stego audio. Or if it is text, then it is stego text. And with the help of some key, which if it is used, it can be extracted and the message can be reconstructed. Okay, so if the text steganography is used, it means that the cover is text. If image steganography is used, then it means that the cover is the image. In today's lab, you have to implement image steganography. And now I will discuss you the fundamental concept of image steganography. So assuming that we have some image. Now, you may have seen, all of you must have seen the images like JPG file or IMG file or PNG file, right? Or bitmap file. These are different file formats. Each of these are actually in next semester you will probably study image processing subject where you will understand it in detail. There are different compression techniques and etc. But for the moment, it is sufficient to understand that image is a file, and if you open that file, you will find a matrix of values, and we are taking simple 4x4 image matrix where the matrix cell represents 1 pixel value. Okay, 4x4 means 16 pixel values are there. We are taking very small image. If you look at the property of your image, if you do right click and see the property of the image file, any of the image file which is there in your hard disk or storage, you will find that there are 1200 cross 800 pixels, right? So that is the property of the image. But we are doing it for a small image, right? Small image, and that is of 4x4. 4x4 means 16 pixels. Okay, and each pixel has this value 50, 25, 49, 79. All these are pixel values. Is it understood? The image format is understood. We can do fopen with image, which can open the image. Okay, and it will give you this matrix, and we are taking a small dimension so that operation can be understood in a proper way. However, it can be expanded for 64 cross 64 and further. Okay, we are taking it for small dimension. Binary information message which we want to hide is 1011 0110 1000 0101. This is our binary information, and we want to hide this. How it can be done, right? Suppose we want to hide this 7th bit 1. See, how many bits are there in the message? How many bits are there? 16 bits. Perfect. How many cells are there in the matrix? How many pixels are there? How many pixels are there? 16 pixels, right? So what we will do, we will smartly hide 1 bit in 1 pixel in such a way that the difference will not be perceptible, right? So we will hide 1 bit in 1 pixel, and this method is called as LSB, least significant bit steganography. Okay, least significant bit. So what is the concept? If we want to hide 7th bit, we will hide it in 7th pixel. This is 1st pixel, 2nd pixel, 3rd, 4th, 5th, 6th, and 7th. So this 7th pixel is a number, the decimal number, which can be represented as binary. Can we represent 78 as a binary of 16 bit binary? In fact, we can represent it by 8 bit. So what is the binary equivalent of 78? What is the binary equivalent of 78? Can you write? Okay, see, this is the binary equivalent of 78. 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0. Right. Now, see, this is our binary. Okay. Now, there are 8 bits. Which bit is MSB bit? First bit from left, that is MSB. Okay. And LSB, least significant bit, is first bit from right. Okay, both are 0 in this case. In this document C, I am showing you the position of the cursor. 0 is underlined, that is our LSB, and this is our MSB. And the technique is hide our bit or information in LSB. How to hide that? What we want to hide is 7th bit. 7th bit is 1, and we want to hide it in the LSB of 7th pixel. So what we will do? We will put that 1 here. So what will be the value after hiding that 1 bit in this? What will be the change? So the binary value will be 0, 1, 0, 0, 1, 1, 1, 1, right? This will be the binary value. Yes, Janil, it is equivalent to 79. So our original pixel value was 78, but we will hide the information so that the pixel value will become 79. Okay, so we are only doing +1. Now our human eyes, that means we are changing the intensity of the pixel by 1, by adding 1. Now our human eye will not be able to find the difference between +1 and -1. Okay, or maybe 0, +0, -0. Right? We will not be able to differentiate it. So for us, even after even after embedding the information, the image will not have significant change, so that the human eye can perceive that it actually contains some hidden information. Okay, now let us consider this second bit, that is 12th bit. What is the 12th bit in the message? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. 12th bit is 0. So we have to hide this 12th bit on 12th pixel. What is the value of the 12th pixel in this matrix? 201, right? But sir, it's some... Yes, so that is there, right? So image steganography and its technique is known, it can be extracted. Yes, that is there. So cryptanalysis is possible, it is not impossible. The question is that this is the simplest technique, and there are many other techniques available, so that it can be made complicated. Like here we are taking the simplest technique, that is 1 bit, but you can use 2 bit, you can use 3 bit. But if you do that, there will be a change in the image, right? So it is possible, it is not impossible. But we are discussing only the basic, simplest technique. Now 201, what is the binary equivalent of 201? Please type. What is the binary equivalent? One 1001. Okay. Now what is the information which we want to hide? 0. So what we should do? LSB should be replaced by this 0. What is the LSB value? 1. And it should be replaced by 0. So what will be the resultant value of the pixel? $200, right? So that you can see here. Okay, in this, look at this in document 11001001. Now this 1 is replaced by 0. So what we'll get is 200, right? So 78 becomes 79 and 201 becomes 200. That will not make much change in the image. So it can be easily protected. I mean, you can easily encrypt and transmit it, right? So at the extraction side, what we have to do, how the extraction is possible. So if you transmit this embedded image, then if you have applied 1 bit LSB, then it is very simple. When you extract, all you have to do is take the LSB value only. So if you take only LSB, it will give you the message. Is it understood? What is the binary equivalent of 51? And whatever is the binary equivalent of 51, take the LSB value as the first bit. Second pixel's LSB is second bit. Third pixel's LSB value is third bit, right? Like that. Is it understood? So this way we can reconstruct the original message. Okay. What if number of message bits is smaller or larger than the binary of image? Number of message bits. Okay, basically you are saying that suppose if we have 64 bit, then we have to take an image of 64 cross 64. So image can be converted into the dimension of the message, or you can divide the message into blocks and send 2 images and then reconstruct so there are different possible techniques. If we want to hide 0 but respective cell is 200, so how we can hide, because after hide cell value becomes same? Very good question, Ronak. So if it is 0 and if you want to transmit 0, then nothing much is required to be done. It is 0. It is good. It is actually beneficial for us that we don't have to perform any operation. Understood? So we don't have to make any change. That information is already there. Right? So if we similarly, if we can also apply 2 bit signal, 2 bits we can hide. So what we can do, instead of hiding, suppose this message bit is 10 which we want to hide. So what we'll do, last 2 bits we can hide. Last 2 bits we can hide. Okay. This way also we can create. But if the number of bits, similarly, if we want to hide 3 bits, then we can create a 3 bit and then we can replace the last 3 bit with those 3 bits. That is 2 bit, 3 bits steganography. But if we keep increasing number of bits in a pixel, the value of the pixel will see the change. And then according to that, the image appearance will be changed because pixel value is changing, right? But normally what happens that 1 bit, 2 bit or 3 bit, they are not making much change. So if we apply 2 bit, then +2 -2 and 0. If we apply 1 bit, +1 -1 0. If we apply 3 bit, +3 -3 0. Right? So 0 +1 +2 -1 -2 is not going to make much change in the image. That is why 1 bit, 2 bit or 3 bit can be applied. Is it understood? Have you all understood the concept? Very good. So now today's lab objective is that you have to implement this steganography, right? So you have to consider, as I mentioned to you, that you have to apply this matrix. Okay. So I will share you the problem statement. Now one more thing. So look at the this second problem. Like you have to hide 1 bit, so you have to take one matrix, hide 1 bit message, and create a embedded output. Then you have to perform the reverse operation also, extract. So 2 operations you have to perform, embed and extract. but also you have to compute mean squared error and peak signal to noise ratio. Now I will explain you what these two things are. So what happens is that if you embed, if you hide one bit information, the output is changing, right? So 78 becomes 79 and 70, 201 becomes 200. So the value is changing, right? So this change in the value is actually uh, representing some error. There is a difference between input image and output image, and that difference is actually error, right? So how to measure that error? Now this is, sir, can we just use Python for this lab? Janil, I am giving you a problem which is very simple to implement either with Python or with C. So if you have used C or C++, it is not really difficult, right? But Python code, if you do Google, you will find it easily. LSB, steganography, Python, everything is available in the Python. So my suggestion is that you don't be afraid of this matrix and everything, because you have already done more complex programs with C and C++. This is not really complex as much as you have already implemented the complex programs. Okay, I have only given you a simplest technique, that is one bit steganography. Okay, that is simplest of that. So you should not find any difficulty in solving this problem. Only thing is that you will have to use it, right? So can you see this screen computing mean squared error and PSNR? Can you see this slide or the web page I have shared with you? Okay, okay. So I was telling you about mean square error. So to measure the difference between these values, this formula is calculated. MSE is equals to summation of for Mn I1 Mn minus I2 Mn, and the difference is taken and it is squared. Summation of all this square is divided by total number of M and N. What is M and N? M and N is number of rows and column, right? So if we take 4 cross 4, then we have to divide it by 16, right? And for each pixel, the output image and input image, what is the difference? That difference and summation and square of that and summation of that square, that is what you have to calculate. That is mean square error. Okay, and with the help of that mean square error, you have to, so if mean square error is small, okay, then it is good. If it is large, then it is not good, right? So MSE represents cumulative squared error between the compressed and the original image, whereas PSNR represents measure of the peak error. So these are two metrics with which we can determine how what is the impact of our encryption on the image, right? So the lower the value of MSE, the lower the error, right? So the less error is good. Okay. So with the help of this MSE, we can apply this formula 10 log base 10 R square upon MSE. Now the value of R, in our case, it is 255. Okay. Just a minute. I will attach my charger. Okay, I have attached my chart now. Okay, so the peak signal to noise ratio. Now these two parameters are also there in the digital communication. So if you want to transmit any signal to from source to destination, if you receive it, you have to measure this PSNR, that is signal to noise ratio. The higher the signal to noise ratio, it is good, right? So if MSE is large, it will become less. If MSE is less, a PSNR becomes higher. And this is exactly what we want. So R value should be taken for 8-bit unsigned integer data, that is R is 255. So in our calculation, we have to take R equal to 255. Okay, it depends upon the kind of data for which we are measuring the error. In our calculation, our data is 0 to 255, that is 8-bit data. So that for that we have to take R equal to 255. Okay, these two formulas you have to use. Is that clear? All of you understood? So you have to write 4 functions basically. First function is for embed. Second function is for extract. Third function is for MSE. And fourth function is for PSNR. Okay, these 4 functions you have to do, and you have to do it for 1-bit image. If I ask you to do 2-bit image, then with little modification you will be able to do it. Okay, you will be able to do it or not? Please tell me. If okay, very good. Image of 1 pixel. It is not 1 pixel. Pixel is 4 cross 4, 16 pixel and 16-bit message. You can take actually 64 cross 64 image. So there are total 64 cross 64 pixels. Okay. But if you take 4 cross 4, how many pixels are there? 16, right? And your message length is how much? Right? So message length we are keeping fixed is 16-bit. Okay, you have to implement this for 16-bit message. So you can take simplest of that is 4 cross 4 image. So that will reduce your computational complexity. That is the only image. But later on, after you complete it correctly for 4 cross 4, you have to expand it for 64 cross 64. Is it understood? That is the fundamental concept of representing any pixel value. Pixel is color. Okay, and we are taking grayscale image. If we take RGB, we have to take into consideration 3 pixel values, 3 values between 0 to 255. That is the representation of color. Okay, fundamental of image. That any image which can, if it is color image, then it is each pixel is having 3 colors, RGB, combination of RGB. Okay. For simplicity, if you use any word processor, you take Word or PowerPoint or any color image related software, and if you select the color, it gives you option to select a color. So you can increase the intensity of the color, decrease the intensity of the color. So when you are increasing and decreasing the intensity of the color, it is actually changing the intensity of this RGB combination. But we are taking only one matrix. Otherwise, per pixel, you have to take into consideration 3 values, RGB, 3 combinations you have to change. Okay. So complexity can increase, but we are making it simple, right? So that your implementation becomes simple. However, it still implements you the fundamental concept of LSB steganography, image steganography. Is it understood? Okay, any doubt, any question? I am putting this material in the classroom in lab 12. All of you will get this link of computing peak signal to noise ratio and MSC lab objective and the document which explains the image steganography. Okay, I am assigning it to all of you. And it is, remember that it is also part of the theory. So this lecture note which I am putting you, that is actually containing other information like monoalphabetic substitution, cipher, and everything. In that page number 12 actually starts with this steganography. Okay, so start page number directly go to the page number 12. So that gives you the description what I have just now discussed. Okay. And I have also provided you the formula, the computing the link, peak signal to noise ratio and mean square error, and the lab objective. Okay. I have given you the problem that hide 1 bit pixel, but if you do complete this in 1 bit, you can also expand it for 2 bit and 3 bit. But that is for practice. Right now, you have to do only for 1 bit. So 4 functions you have to implement: embed, extract, MSC, and PSNR. Is it understood? All of you have understood the problem statement? Any doubt, any question? So you can start now implementation. And this concept is part of syllabus also. Okay, sessional exam syllabus also. For image processing related implementation, while C and C++ are good programming languages, uh, there are other languages and other tools available like MATLAB and Octave. MATLAB is by MathWorks, and Octave is open source tool which is similar to MATLAB. But similarly, there is a Scilab, 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 which is MATLAB equivalent of provided by open source community. So these three different tools are used, and its programming languages are used for image processing related implementations. So as somebody said, Python. So Python is also useful, right? So it is in general, these are the programming languages which are used extensively for image processing, right? This for your additional information. $255. Refer to the document, it is mentioned. It is mentioned in the document. Have you gone through that document which I shared with you? That is the definition. Okay, you have to accept it. So right now we are not going into the detailed concepts, right? It is the formula. Highest intensity value is R, right? In our case, it is 255. So as it is provided by the definition, you can see in the document which I shared with you. See what is mentioned, that R is the maximum fluctuation in the input image data type. For example, if the input image has a double precision floating point data type, then the R is 1. If it has an 8-bit unsigned integer data type, then R is 255, right? Only PDF file with code, no handwritten is required in Lab 9 onwards. R is fixed. R is not a difference. M, so MSc actually calculates the difference. Priyank. R is 255. It is written in the document. Janil or Ronak asked the same thing. Yeah, Janil has asked the same thing. Got it? R value is 255. It is given in the document. See, what is MSE? MSE is representing error, mean square error. The name suggests mean square error. So we calculate error, take a square and take a mean of that. Okay, that is error. Signal to noise ratio. PSNR means signal to noise ratio. So in a communication system, there is a concept of a signal and noise. Okay, anything which you are transmitting over wired or wireless channel, that is actually signal. Okay, so signal has amplitude, frequency, right, phase. So it is represented, signal is represented as a combination of amplitude, frequency, and phase. Now, noise is something which actually is unwanted signal. So if you have, suppose your message is having signal with some amplitude, or say, let's say your signal is some message, or this is noise is the effect you all must have experienced when you have tuned into radio. So in radio, when you are tuning it to a particular frequency, below or after that frequency, you get some noise disturbance, right? So that is a noise which is unwanted. Now, signal to noise ratio means how much signal is present and how much noise is present, right? If you take the ratio of that, signal to noise ratio, and there is a formula for that, standard formulas are available. So here what we are doing is that we are computing it peak signal to noise ratio. Noise is our error, right? And signal is our highest value. That way we can interpret it, right? So if it is, if the ratio, if MSE is higher, signal is going to be the lower. If MSE is low, signal will be high. Desirable thing is low error, high signal. Is that clear to all of you? Any of you have completed embed operation? Embed operation, any of you? Okay, can you share in your screen? Ronak? Yes, Ronak, you can use your mic also. Font are not visible in code. If you can enlarge it, it would be better. I think you are not audible to me, or you are speaking anything?
Yes, sir. Audible?
Yes, yes, you are audible to me. Okay,
Yes, sir. So
go ahead.
this is our no, sorry. This is our binary message.
Okay, can you enlarge the font size? I'm not able to read it.
Now,
Still little with little difficulty, but it is still readable. It is readable, but with little difficulty. If it is possible, enlarge it further.
now,
Now
sir.
it is up. Now it is good. Good. Okay.
This is binary message, and this is our static cover. And using this embed using LSB method, we get stego object.
Okay.
So this is our embedding code.
Okay. Where is the
So
operation you have implemented?
yes, this is embed using LSB.
Okay. So you are embedding bit by bit, right?
Yes, sir. And return a 2D object which is modified by this function.
Okay. And show the output.
Yes, sir. This is my binary message. This is embedded matrix, 2D matrix.
Okay. So you show original and embedded both so that the difference can be visible.
Yes, sir.
Okay, so that it can be easily understood that okay, original image is converted into this embedded image.
Yes.
And
And
the
this
same
is
way
our
you can
extracted
print
message.
extract and the reverse operation. Okay.
This is extracted message, which is same as this binary message.
Yes. So what I'm saying is that extracted message and binary message are same, but in extract operation also you can print this same matrix tables. So it will clarify that you are actually, in fact, in
But this
extract
matrix
we want
tables is
only
not
message.
modified in extraction. So this is not much difference in matrix table.
Yes, you are
So
right. In extract we need only message only, so nothing much is
yes,
required. Oh, so it is
yes,
good.
and this is mean square error, and this is
Where you have calculated mean square error 0.25, okay, and 54.15.14. Very good. So this actually completes a 1 bit hiding message for 4 cross 4. Now expand it for 64 cross 64.
yes, sir.
Okay, but it is a good effort, and you have completed this task. I have kept it less complex because many students are finding it difficult to implement. So I have kept it complex less. But since you have completed it, I encourage you to increase the complexity and make it for 64 cross 64 matrix.
Yes, sir.
Okay. And then you go for 2 bit. Okay.
Yes, sir. Can you stop?
Yes, yes. Good. Ronak, which operation you have used to replace the LSB value? In embed, what you have done for coding purpose, how you have added the last bit, changed the last bit?
If last bit is not same, then we need to replace.
Okay, and if you want to apply some mathematical formula, then binary operation, if you want to perform, then how it can be done? Instead of
Means
replacement, if you use some binary operation, then how it can be done?
means integer to binary conversion.
No. Binary to see your message, your pixel value is in binary, okay?
Yes, sir.
And last bit you want to change, and you have
So
to change it by applying some binary operation. Then which operation you will perform?
so first we convert particular cell value to binary, then we convert to last bit to respective 1 or 0, and then again convert to integer value and then
No,
store to
I'm
this.
saying that no, we are forget complement. Okay, so Janil has understood the question, but he is saying complementing it.
Yes, sir. If
Complementing.
0 and 1, then we replace 0 to 1, or if 1 to 0, then we replace to 1 to 0. Yes.
Let us see the general solution. If message bit is 1 and pixel mode 2 equal to 0, then add it. Okay. And else if it is 0 and pixel bit is 1, then reduce it. Fine. But binary operation, you are doing still plus or minus. Binary operation. XOR will give you the desired result. Okay. So think about it. Janil, okay. So these are different options. We have found different options like Ronak has done correct thing. It is not wrong. All I am saying is that if you could do it with binary operation, then it would be a better one. But fine, I mean, we have found different options and you can explore these options. So it will actually increase your programming practice. But good that some of you have done in a different way. Anyone else has done implementation is over and would like to show? Anyone else wants to share your screen and show your result? So we are approaching towards the end of the semester. There are some students whose lab submission is pending and its information is available in the classroom, and some of you I have also sent personal emails also. So please submit your submissions. Uh, please share this information to your classmates. There's, if they have any pending submissions, earlier pending submissions, that please finish it at the earliest by next week if possible. Anybody who has completed the program or at least embed phase? Yes, Keval, can you share your screen?
Sir, is screen visible?
Yes, it is visible.
Sir, here is the program. I'm showing you the output.
You will please little bit zoom.
Yes, ma'am. Just a minute.
Okay.
Just copy the input. That's why I have. Ma'am, here I am expecting the cover image elements, so that why here I am entering that. And once it is entered, then we need to enter the binary message So that is also I want to go. Let me write. So 1, 2, 1, 2. Once it is entered, then I'm printing this Stego object, then this extracted message, then MSC and PSNR value.
Okay.
Good.
Can you show the code?
Yes, sir. Just a minute. Sir, here I am scanning the input, binary message and that. Then when I'm calling this embed function, then extract function, then MSC and PSNR.
Okay.
And this is the embed function, sir. Here is the condition to replace the bits LSB and MSB.
Okay.
And in this extract function, we just by the LSB bit we can consider our that extracted message should be 0 or 1. This is the extract function and this is MSC function. And this one is PSNR.
Okay. So now you can do it for 64 cross 64.
Yes, sir. Just here I have to change instead of a dimension 4, I need to change it to I think 64. That means 16, and here I can take 64. That is how this whole program works.
Okay. So test your input and output for
Yes,
64 cross 64, all of you. Okay.
Okay.
Now once you all complete for 16 bit, you can you should do it for 64 cross 64. So in the final program submission, do it for 64 cross 64.
Okay, sir. Okay. Can I stop present, sir?
Yes, yes. Thank you.
Okay. Thank you.
Okay, so I think most of you could do it as lab time is about to end. You may leave, take a break, and join your regular teaching at appropriate time. You may leave now if you want.